Hi guys, welcome to another chemical engineering tutorial brought to you by the ChemEng student. In this lesson we're going to take a look at the analysis for degrees of freedom, and we're going to consider single and multiple units. So the question here is, what is a degree of freedom? Essentially, a degree of freedom is a method in which we can evaluate if a given system has enough or too much information in order to be solved. Now, this analysis method allows for a quick verification if the data that is provided is substantial or not. Now, it's key here to note that this isn't a method of actually determining the unknown variables. The degree of freedom analysis is simply a way to check, do we have enough information in order to solve the given problem, before we start to waste our time beginning to solve the problem and then realise halfway through that we can't actually solve the system. Now, degrees of freedom analysis is especially useful when we have multiple units with multiple variable systems, because these can often involve complex and intricate calculations, because within multiple unit systems, or indeed with multiple variable systems, whereby there's maybe relationships between some of the streams, some of the components, then each unit can be a function of the previous unit. So there is also a set of underlying conditions that the degree of freedom analysis will allow us to determine before actually beginning the calculation. Now, the equation here is based on determining the number of unknown variables, or the unknown equations, the number of known equations or variables, and then any other additional correlations that we are provided within the question statement. So the general formula that we use for degree of freedom analysis is as follows. So degree of freedom is equal to the number of unknowns minus the number of independent balances that we can carry out, plus the number of other equations or correlations that we have been provided in the question statement. Now, there are three sets of conditions that can arise from carrying out the degree of freedom. So the first one is that if the degree of freedom, when we perform this calculation, if the DOF equals 0, then we have a system that we can solve. We will be able to solve the problem. If the degree of freedom is greater than 0, then we have an unsolvable system. Because if we look at this equation, then we don't know enough information compared to the amount that the number of unknowns isn't equal to the number of known data points, data variables, data equations. So therefore we have an unsolvable system. Now, if the DOF is less than 0, then this means that we have an overspecified system, in that we have too much information compared to the number of unknowns that we're trying to find. Now, this can sometimes be okay in the sense that if the information isn't conflicting, then this would be a suitable system, but we always try and aim for the DOF of equal to 0, because when we have an overspecified system, then what can sometimes happen is, say for example, we determined that, say in this case we had x plus 5 equals y, but then we had x minus 2 equals y. Then essentially here what this is saying is that we have contradictory statements here. So we would need other pieces of information in order to be able to solve this, because this conflicts with each other. So this is what would arise with an overspecified system. This is just a very basic example. We'll look at proper examples of DOF in just a second. Now, when we carry out DOF analysis, it's important to remember that the key variables and parameters that should be accounted for. Now, this is a list of the most common variables and points to remember. So when we are about to conduct degrees of freedom analysis, these are the sorts of things that we need to consider. So we need to account for the number of different species. Now, that is the number of different components. So if we have a system that contains A, B, and C, then we have 3 different species. Now we can also find relationships between flow rates, or indeed the mass or mole fractions. Now there also is relationships we can have with the physical properties. Because say for example we are working with gases, then we can have relationships in terms of, say, the ideal gas law. Then if we can have a relationship between the physical properties of the different species, then that would give us an additional term of known variables. Now the summation rule is very, very important because that will allow us to create a subsequent relationship that may not be obvious or present in the problem statement. Then if we have any other given piece of information that is specific about a species relationship, say for example we said that A goes to 2B, then we know that B is double the amount of A. So that's a relationship between the species A and B. Now, sometimes we can be provided with system limitations and also some constraints, and we can use these to our advantage. Now let's take a look at a working example here. Now this is for just a single unit system, and it's asked us to determine if the following system is solvable with the given data that is provided. So what we need to look at here is we need to see how many unknowns we have, how many knowns we have, and if we have any other additional equations or relationships that we need to account for. So by looking and analysing the data that we have, we can see here that we don't know the composition of the top stream. We know the flow rates of the inlet and the top product, but we don't know the compositions. So we have 2 unknowns here. So this is number 1, this is number 2. And then here, we know the composition of the bottom stream, but we don't know the flow rate of the bottom product. So this would be number 3. So the number of unknowns is 3 in this case. Now the number of knowns will be minus 3. Okay? Because minus, remember the equation is the number of unknowns minus the number of knowns and then the number of additional equations. So we have 3 known species because we can create 3 balances. We can do a balance on component A, we can do a balance on component B, and we can do an overall balance in terms of the flow rates. So we have 3 knowns. Now, number of other equations, we aren't provided that. So when we perform this calculation, 3 plus minus 3 is going to give us 0. So that means we have enough information. It's not an overspecified system and we don't lack information. We have enough that we can solve for this system. Now example 2 is something very similar, but we have some changes to the information. This time, we don't know the composition of A coming into the system, but we do know what the composition is on the bottom product. However, again, we still don't know the composition of the top product. We know the flow rate. We still don't know the flow rate of the bottom product, but we know the composition. And we don't know the composition of A. So the number of unknowns this time is 4. Now the number of knowns is still going to be the same because we have the relationship, the balance on A, the balance on B, and the overall balance on the flow rates. Now, as it stands just now, it isn't clear, but we don't have any other equations. So therefore, our value for the degree of freedom analysis is 1. So we have an under-specified system. We don't have enough information to solve this problem. So let's think about it again. The number of unknowns is fixed at 4. The number of knowns is still fixed at minus 3 because we don't have any additional species. We still have A, we still have B, and we still have the overall flow rates. However, one thing that we didn't consider here is the summation rule. We can perform a summation rule here and determine outright the relationship between A and B. And this would give us our other equation. because we know that the composition of XA0 plus XB0 equals 1. That is a given equation. That's the summation rule of the given streams. So because we know this, we could actually work out what A0 is first. So what that will be is that will be another equation. So we have -3 plus -1 is -4, plus 4 gives us 0. So now, by exploiting the summation rule, we are actually able to carry out this calculation. And that's sometimes the secret to some of these questions, is trying to find additional correlations if it isn't given or isn't clear in the problem statement. Now, multiple unit systems, this is where it can get a bit more involved. And systems that involve multiple units will require some thought before beginning the material balance or even the degree of freedom analysis. Now, we sometimes have a series of trial and error calculations that we need to do, which would allow us to determine the correct starting point. Because as we know, that the degree of freedom analysis allows us to quickly identify if a problem can be solved. With multiple units, this allows us to determine what the starting point is, and that will be possible to solve. So it sometimes appears as though we have enough information to the problem to begin with. However, in reality, we actually don't. So we need to work out which unit is our best starting point. Now, in the next example, we won't actually carry out the material balance. We're just going to look at the degree of freedom analysis. However, if you would like to see how the overall material balance is conducted, let us know in the comment section and we'll make a subsequent video on how to actually solve more complex material balances. So example 3 gives us a mixing unit receives two streams, one that contains equimolar amounts of water and methanol. The other has 10 moles, of which 48 mole% is aqueous methanol. So that means the other amount will be 60% water. Now the mixture enters the first separator to produce two new streams. The top product contains 70 mole% methanol and the remaining being the water. Now the bottom stream contains 70 moles and enters the second separation unit. Now the top product contains equimolar amounts of both compounds, so that's in the second separation unit, while the bottom stream flow rate and composition is unknown. Now, assuming an initial basis of 100 moles of the fresh feed to the mixer, we need to determine the most appropriate starting point in order to carry out the material balances, and we need to justify our answer. So we can't just turn around and say this is the best one. We need to justify it by carrying out the degree of freedom analysis. So let's highlight the schematic here. So we have our mixer, so we can call this M. So this is our mixer. This is separation unit 1 and this is separation unit 2. So what we'll do is we'll go back through the information and we'll start to annotate our schematic. So we know that we have a basis of 100 moles of fresh feed to the mixer, and that has equimolar amounts. So we have 0.5 for methanol and 0.5 for water. Now the other stream here is 10 moles, and that has a 40% methanol and 60% water. So that is at this point. Now the mixture here enters the first separation unit to produce two new streams. So the top product, in this case, contains 70 mole% methanol, so therefore we have 30% water. Now the bottom stream contains 70 moles, so that's technically our flow rate. Now we then know that the top product of the second separation unit has equimolar amounts. So we have 0.5 for water and 0.5 for methanol, because remember you can do the summation here and say that 0.5 plus 0.5 equals 1. Now here, we now need to understand and determine the number of unknown variables we have within this given system. So the first thing that we don't know is we don't know what the flow rate is coming out of the mixer which comes into the separation unit number 1. So you can see that they're all sort of related to each other or precursors of one another, because the flow rate here links the mixer and separation unit 1. So we need to know the flow rate. Then we don't know the composition. Now what we'll do is we'll use a basis of methanol, because we know that for water it would just be 1 minus this. So we'll keep things simple and we'll do it just in terms of the methanol. So what we have here is Y1M. So the subscript 1 meaning stream 1 and M standing for the methanol. Now we now don't know the flow rate of the top product from the first separation unit. We know the composition, but we don't know the flow rate. So that's our third unknown. We therefore don't know the composition of the bottom product out of the first separation unit. We know the flow rate, but we don't know the composition. So that's the fourth unknown. We don't know the flow rate of the top product from the second separation unit. So that's our fifth. We don't know the flow rate of the bottom product, that's our sixth. And we don't know the composition of the bottom product from the second unit. So that tells us that we now have 7 unknown variables. Now we need to consider the following locations to carry out degree of freedom analysis. So we need to do the overall balance. So that's us looking at the entire system and asking ourselves what comes into the system and what leaves the system. We then will carry out a balance on unit 1, so this is this one. We'll then carry out a balance on unit 2, which is this one. And then we'll carry out a balance on the mixer, which is here. So we need to do these one at a time. We'll determine what the degree of freedom is for each unit, and then based on their values, we'll determine what the best starting position is. So let's take a look at the overall balance first. So that is essentially saying what is coming into the system and what is leaving the system. So the number of unknowns here is going to be N2, because we don't know what leaves here. N4, we don't know what leaves here. We don't know what leaves on the bottom product for separation column number 2. And we don't know the composition of that stream. So here we have 4 unknowns. Now the number of knowns here is that we have 2 balances. Now one thing that we need to note here is that we know that the streams of N2 and N4 are equal to each other. So that's an additional piece of information that we should have mentioned before, but that's an additional piece of information that we know here. So we have the 2 balances, which is the balance of our species, and we know the relationship between N2 and N4. So that means we have 3 knowns, 4 unknowns. We have a degree of freedom of 1. So we don't have enough information in order to solve this problem. Now let's take a look at unit 1. So we'll do the balance around here. So the number of unknowns this time is we don't know what the flow rate is coming in. We don't know the composition coming in. We don't know the flow rate of the top product, and we don't know the composition of the bottom product. So we still have 4 unknowns. Now we can perform 2 balances because we have 2 species. So we can do a species balance on each. And that tells us that our degree of freedom this time is 2. So this is even worse than the overall balance. Now let's take a look at unit 2. So exactly the same principle as before. We will consider only the unit 2 what comes in and what leaves. So we know what comes in terms of flow rate, but we don't know the composition. Then we don't know, so this should be 3, not 2. So we don't know the composition of the inlet. We don't know the flow rate of the top product. We don't know the flow rate of the bottom product, and we don't know the composition of the bottom product as well. So we still have 4 unknowns. Now the number of knowns in this case is still just going to be the 2 species balances between water and methanol. So again we have a degree of freedom of 2. So far, this question is impossible to solve. We don't have enough information. We can't solve here, we can't solve here, and we can't solve overall. So if this problem is to be solvable, we need to be able to balance around the mixer. So the number of unknowns this time is we don't know the flow rate coming out of the mixer, and we don't know the composition coming out of the mixer. So two unknowns. The number of knowns is going to be the two balances. So we have the balance on methanol, we have the balance on the water. So 2 minus 2, that will give us the degree of freedom of 0, which means in order to begin the question and solve this problem, we can therefore start at the mixer. Because, let's think about it, when we use the mixer, we'll then be able to determine N1 and Y1M. So that will take two unknown variables from this separation unit. And we had a difference of 2 in unit 1. So now we have two unknowns, two knowns, we can solve the system. So that's the process on how you would carry out degree of freedom analysis on each different unit and the overall system. And this allows us to determine that our starting point must be for this system on the mixer. So that's the end of this lesson. Thanks for watching. Hopefully this was helpful in understanding the idea and the procedure for calculating and determining the degree of freedom analysis for both single and multiple units. If you liked this video, please like and subscribe to the channel. It really helps us reach as many chemical engineering students as possible. Thank you for your time, and we hope to see you in another video.